In the last episode, we watched a perfect startup, permissives, field flash, ignition, synchronization, all in order. But equipment doesn't stay perfect forever. Today, we look at what actually breaks, the failure modes that turn a routine start into an unplanned outage, and why utilities across the world are replacing these systems before that happens. Start with the thyristors themselves, the solid-state switches at the heart of both the SFC and the SEE. Every start cycle pushes them through a burst of thermal stress, cold, then suddenly carrying hundreds of amps. Over thousands of cycles, across decades, that stress fatigues the silicon and its internal connections. A thyristor doesn't usually fail gracefully. It fails as a short or an open circuit, and a single failed device in a series stack can take the whole bridge down with it. Next, cooling. These systems are air-cooled, and that means filters. Blocked filters starve the cabinet of airflow, internal temperatures climb, and every component inside, thyristors, control cards, capacitors, ages faster than it should. A failed cooling fan is often the quiet precursor to a much bigger failure, weeks or months later. It's one of the simplest things to inspect, and one of the most commonly neglected. Then there's the control electronics, and this is where obsolescence really bites. A real, public case. In 2024, a static frequency converter that had been running for 25 years failed at a power plant. The control cards inside were long out of production. No spares existed anywhere. The original manufacturer no longer supported the platform. The plant was forced into an unplanned outage, not because the concept failed, but because nobody could source a replacement card for a system built in the previous century. This single story is why so many utilities are upgrading now, proactively, instead of waiting for a failure to force their hand. There's also a purely mechanical wear point, the slip rings and brushes. Remember, static excitation feeds DC current onto a spinning rotor through physical contact. Brushes wear down. Slip ring surfaces can pit, groove, or accumulate carbon dust. Left unchecked, this leads to arcing, uneven current transfer, and eventually, a field circuit fault. It's mechanical maintenance hiding inside an electrical system. Easy to overlook if you only think in terms of electronics. And finally, communication faults. These systems don't operate alone. They talk constantly to the plant's control system, over hardwired signals and serial links. A corroded terminal, a firmware mismatch after a partial upgrade, a protocol that's no longer supported. Any of these can silently break the conversation between the SFC, the SEE, and the DCS, even while the power electronics themselves are perfectly healthy. Here's the pattern across every one of these failure modes. None of them announce themselves loudly in advance. They accumulate quietly, one degraded fan, one aging thyristor, one obsolete card, until the day the plant needs to start and can't. That's the real cost. Not the failure itself, but the outage, the lost generation, and the emergency scramble that follows. So, thyristor fatigue, cooling neglect, control card obsolescence, mechanical wear, and communication faults. 5 ways a startup system quietly ages toward failure. Next episode, the final one in this series. How a real retrofit project actually happens, from survey to commissioning. Subscribe, and I'll see you there.